Derivatives of trigonometric functions. So far, we've talked about taking derivatives of polynomials. However, what about other functions that exist in mathematics? Well, next we're going to explore the derivatives of trigonometric functions. For example, if asked to take the derivative of y equals the sine of x, our previous rules wouldn't apply. Since those rules of polynomial functions don't apply to trigonometric functions, we have these special derivative rules. The derivative with respect to x of sine of x is equal to cosine x. The derivative with respect to x of cosine x equals negative sine of x. The derivative with respect to x of tangent of x is equal to secant squared x. The derivative with respect to x of cosecant of x is equal to negative cosecant x times cotangent of x. The derivative with respect to x of secant x is secant x tangent x. And the derivative with respect to x of cotangent x is negative cosecant squared x. Memorize these derivatives because they often show up on different standardized tests. A key to study or an idea for studying is to make some flashcards. Let's take a moment to prove one of these derivatives. The derivative with respect to x of sine of x is equal to cosine x. We're going to start with a few limit definitions that we have with some trig expressions. So recall that the limit as x approaches 0 of sine x over x is equal to 1, and the limit as x approaches 0 of 1 minus cosine of x over x is equal to 0. So we're going to use these two facts along with the limit definition of what a derivative is to prove that this is true. Let's start with what the definition of a derivative is regarding limits. So the derivative with respect to x of sine of x can be rewritten as the limit as h approaches 0 of sine of x plus h minus sine of x all over h. And then we can rewrite this as the limit as h approaches 0 of, and if we remember, the angle sum identity with sine of two angles that are added together can be rewritten as the sine of x cosine of h plus cosine of x sine h, and then we still have the minus sine of x here all over h. And now, using the commutative property of addition, we can reorganize our terms that we have here. We want the two terms that have sine of x with them, or next to each other. And since subtraction is just adding a negative, we can still rearrange it. So let's actually make the middle term our first term, the last term our second term, and our original first term the last one. So that can be rewritten as the limit as h approaches 0 of cosine of x sine h minus sine of x plus sine of x cosine of h, and then all over h. So let's rewrite our beginning. Now let's look to see what we can simplify. Notice our second and third terms here both have a sine x in it, so I can factor that out. And in order to get the 1 minus cosine of x over x, or 1 minus cosine of h over h, we're going to factor out a negative sine x. Then that way this sign changes. So our first term stays the same as cosine of x sine h. but then we have minus sine of x, and that's what we're factoring out of both of these terms. And when I pull it out of the first one, I'm left with simply 1. And then for my second term here, it's going to be minus cosine of h, and then all of this is over h. Now we can split this up into two separate fractions and take the limit of both of them. So that would be the limit as h approaches 0 of cosine x sine h over h minus the limit as h approaches 0 of sine x times 1 minus cosine of h over h. And now we know that sine of x over x is equal to 1. So that means that the sine of h over h is also 1. So this cancels out. And then we have 1 minus cosine of x over x, or 1 minus cosine of h over h, is equal to 0. So this entire term cancels out because we had that identity here is 0. So therefore we are left with the limit as h approaches 0 of cosine of x, which just simplifies to cosine of x. So we've proven this identity. And this slide basically proves exactly what we just proved, that the derivative with respect to x of sine of x does indeed equal cosine of x. If you would like to see proofs of all of the other trig derivatives, you can find them by researching them online. Similar to derivatives of trigonometric functions, the inverse trigonometric functions also have derivatives. So we have, if y is equal to the inverse sine of x, then the derivative of y with respect to x, or the derivative with respect to x of the inverse sine of x, is equal to 1 over the square root of 1 minus x squared, and that's when the absolute value of x is less than 1. And then if y equals the inverse secant of x, the derivative of y with respect to x is equal to 1 over the absolute value of x times the square root of x squared minus 1. And that is true given that the absolute value of x is greater than 1. For inverse tangent, the derivative of inverse tangent with respect to x is 1 over 1 plus x squared. And then if y is the inverse cosine, the derivative of y with respect to x will be negative 1 over the square root of 1 minus x squared. And similar with sine, this is only true with inverse cosine given that the value of x, the absolute value of x, is less than 1. And then for inverse cosecant, the derivative of that with respect to x is negative 1 over the absolute value of x times the square root of x squared minus 1. And that's provided that the absolute value of x is greater than 1. And if we're taking the inverse of inverse cotangent, the derivative of inverse cotangent with respect to x is equal to negative 1 over 1 plus x squared.